Okay, you have probably read the properties of real numbers. You can find them in just about any algebra book. Commutative property, distributive property. Although I have to be more specific when I say commutative property, I mean of multiplication or of addition. Distributive property, there's only one from multiplication onto addition. Um, you can read them from any book, any algebra book. I want to emphasize how important and how we use them um, extensively in mathematics. So let me give you some examples of how we use them extensively. Instead of just naming them, for instance, when you have something as simple as this, 7 times the quantity of 5 plus x, and we just move this, can we move the 7 to the other side of the parenthesis? And the answer is sure, we may. And right there, we're using a property. We're using the commutative property of multiplication. We have to know the names of the properties, and we have to know how, when they are being applied. So here, we are multiplying 7 times a quantity. When we put the 7 on the other side, that means that we're applying one of the properties of real numbers. And by the way, by properties of real numbers, we mean the properties relative to the operations of addition and multiplication. Real numbers have many properties. For instance, they are very dense. That means whenever you have two different numbers, there's a number in between. There's no gaps in between two real numbers. There's a continuity through the real number. So there's plenty properties of real numbers. When we talk in algebra about properties of real numbers, we mean the operational properties when we use multiplication and addition. For instance, we also have the distributive property that allows us to put this down as 5 times 7. Well, that is 35. And then, see, technically speaking, we have to do x times 7 if we change that around. If I want to change that to the other side, then we have to apply the commutative property of multiplication. And if I want to move this 7x to the other side, then I have to apply the commutative property of addition. Of course, we have the distributive property. We didn't have to go through all of that. I kind of messed up at the beginning. I didn't mess that up. I made this longer than it had to be. But the purpose of this was to show that even when we do something as simple as that, we are applying properties of real numbers. Something else I want to mention is the way this notation works. This is telling us that this is equal to that, which in turn is equal to that, which in turn is equal to that, which in turn is equal to that. So we are using a combination of line notation and column notation. So, and that is okay. This is just a long chain of equations where we are stating that this is equal to this, which in turn is equal to that, which in turn is equal to that, which in turn is equal to that. And again, to go from here to here, we applied the commutative property of multiplication, distributive property of multiplication onto addition. Then we applied the commutative property of multiplication, and then we applied the commutative property of addition. Now, this was unnecessary to go through all of those steps. It was completely unnecessary because we could have gone from here to here just by using the distributive property of multiplication onto addition. Yes. But let me show you some other example that is not as obvious. For instance, if you have 7 times the quantity 5x, okay, we know how to handle this because everybody tells us the shortcut. The shortcut is just multiply with a 5 and you get 35x, and that's the answer. But I want to show you what is going on behind the scenes. technically speaking, we have to use the associative property of multiplication. So here we are multiplying three things together: the 7 with the quantity of 5 multiplied with x. So there's a multiplication going on here, and there's a multiplication of the 7 times this quantity. So if I want to multiply the 7 with the 5, technically speaking, we have to go and multiply 7 times 5. We have to reassociate this multiplication. This multiplication, as written, says we have to multiply with the 5 and the x, and then the result of that has to be multiplied with the 7. Well, technically speaking, we have to reassociate in order to multiply the 7 with the 5. So we apply the associative property of multiplication. Then we multiply those two numbers out. So that's going to give us 35x. Most of us will skip this, but if we call you for figuring out what property is being used from here to here, we have to be able to tell, oh, we're using the associative property of multiplication to go from here to here. And only then we can multiply the 7 times the 5 and then have 35 times x. Now, in practice, if I'm asking you to simplify, you don't have to go through this. Only in certain problems, I will ask you to actually go through the steps one by one. But in general, that won't happen all the time. It's only in maybe some parts of this. Yeah. Example 3 is even more complicated. Let's say you want to add two polynomials, 3x plus 5. That's one polynomial which we want to add with 7x plus 4. 7x plus 4. So I'm going to write this as a column because this is too long to put as a line and then break it down into a column. All right. Now, most of us know the shortcut, and we know the answer. The answer is going to be 3 plus 7 of the x's, so that's 10x plus, and then the 5 and the 4 make a 9. So I'm just going to write on a different piece of paper the answer. I'll just use this piece of paper. The answer is 3x plus 7x, 10x plus 5 plus 4, which have no x, 9. And that's the way most of the time, 99% of the time, that's the way we're going to obtain this addition. However, I want to do it the really, really long way just to show you the kinds of properties we are applying when we're adding these polynomials together. Yeah. So the first thing we should do is perhaps multiply, or rather add the 3x with the 7x, which means we have to first perhaps reassociate this. So we can use the associative property of addition. All right, so 3x plus 5 plus 7x, I want to put those two together. This is a generalized form of the associative property of addition, plus 4. So we have three terms, 1, 2, 3. Yeah, this is a little confusing. Please bear with me as I explain this. In the examples that you're probably going to work on are going to be way simpler. I just want to show you how bad this is if we approach it strictly from the properties, the basic properties of real numbers. Okay, then we use the associative property, rather the commutative property of addition to flip those two around. So this is 3x plus 7x plus 5. Keep the 4. The 4 is waiting while we continue with this. Then reassociate this. So 3x plus 7x. Keep the 5 out, waiting. And we, technically speaking, we cannot add those two until we reassociate again. This is going to be, of course, 10x plus 5. We need to add the 4. And technically speaking, we have to reassociate that. So we're using associative property of addition to write 10x plus 5 plus 4, and that's going to give us 10x plus 9. So if we were to use all the properties one by one without actually jumping properties, doing 2 or 3 or 4 properties at once, we have to go through pretty much all of this. So reassociation by addition, and actually this is a more generalized than it had to be. I mean, we're using a property that is even more general because we have 4 terms that we are reassociating. Then what did we do? We used the commutative property of addition because those two got flipped. And then we reassociate again. So instead of the 7x plus the 5 added together first, we're going to add the 3x plus the 7x, keeping all the terms together. I mean, in the same order. And then we add those two, finally. But now the 5 and the 10x are together, and we really want to have the 5 and the 4 together. So we have to reassociate. Yep. And then we finally get to this answer. So when we start with this problem, and we jump from here to here, we're not doing anything wrong. We're actually taking a shortcut. We're just adding like terms together. But behind the scenes, there is a lot of stuff that is going on. And that stuff is precisely the properties of real numbers. The commutative properties, which are 2 of them, the associative properties, which are 2 of them. We have the distributive property, which we could think of them as 2 of them, because we could distribute from the left onto the addition, or we can distribute from the right, as we did in this example. And then we have properties of units. There's a unit in multiplication, and there's a unit in addition, in the operation of addition. So let me write more properties, or rather more examples. When we have, for instance, 3 multiplied with 5 and divide by 5, well, we know what's going on. We can, so technically speaking, we have to multiply those 2 first and then divide. However, pretend that is a variable, so we wouldn't know what the actual product would be. I just want to keep things simple. Yeah, this gets a little more complicated, but this is the same thing as 3 times 5 divided by 5, which is the same thing as 3 times 1. And the property of 1, it may sound obvious, but 1 is very crucial in algebra, because when we multiply with another number, that multiplication preserves the other number. So that is equal to 3. Now, in practice, 99% of the time, we're just going to cross that off and not worry about all of the other stuff. But technically speaking, what's going on is that eventually we're multiplying by 1. Another way to think of this is to say, well, we're going to multiply by 5 and then divide by 5. And those two undo each other. Those two things that we are doing to the 3, which is multiply by 5, to then divide by 5, undo each other. Watch out for examples like this. If you have the reciprocal, so the 3 and the 5 on the denominator and the 5 on the numerator, well, things to simplify. Yeah, but there's an absence of a 5 via multiplication, and the absence is 1. The absence of a multiplication is 1, not 0, but 1 when the operation is multiplication. And in this case, we have a multiplication going on, 3. Yeah. So watch out. If you are simplifying factors, things that we multiply together, but there is a denominator that is not equal to 1, then the denominator has to stay in the denominator of the fraction. If there's a factor that is not equal to 1, that's what I meant to say, then that factor has to stay in the denominator of the fraction if the factor is in the denominator to start with. Also, we have examples like this: 3 plus 5 divided by 5. Of course, it is very, very incorrect, very wrong to simplify the fives as we did up here. So the answer is not 3. Um, and the reason is because the operations are different. Here we're adding 5 to then divide by 5, and the addition and the division are not undoing each other. So this is simply 8 divided by 5, and then we just leave it like that. There's nothing really to simplify after that. So we gotta watch out what happens with our problems. The best thing to do, in my personal experience, is to develop what I would call muscle memory. You start working problems until it becomes second nature, when you can do certain things and when you cannot do other things. We're going to talk about properties of exponents later on in a different video. But I wanted to show you the properties that are used in one of the properties of exponents. Yeah, this is a chain of properties that we will see. So let's say you have a, b quantity squared, and one of the properties we will see later in another video when we look at exponents is that we can distribute the exponent and have a squared and b squared. This is a fact. This is true. This is a property of exponents. Okay, so property of exponents. However, this property relies on properties of real numbers, and actually showing how this works out is not trivial. Let me show you. Again, there's a lot of stuff that is going on behind the scenes, and it is good to take shortcuts. I'm not necessarily against that. We just got to understand that there's a lot of things going on when we take shortcuts. So AB quantity squared really means AB and then AB multiplied together. That's what the exponent does. And then we have to, if we want to rewrite this, we have to reassociate via multiplication. So we're going to use the associative property of multiplication. Anyway, I'm going to use a generalized property of, or associative property of multiplication. There's really, even though I'm showing you step by step, I'm still using some shortcuts, which is very, very interesting. So BA, so I'm still have them in the same order, A, B, A, B, A, B, A, B, except that now they're associated differently. We're going to do BA first. Actually, technically speaking, we should have here, because multiplication is a binary operation. We only multiply two things at the time. So this means we're going to multiply BA first, then the product has to be multiplied A first and then BA, whatever that is. And then after that, we're going to multiply that product with B. Yeah. Now we can use the commutative property of addition. So this is really A times A, B, close parenthesis, close the other grouping symbol, B. And then those two we have to put together. So we reassociate A, B, B. Okay, that is A squared, B, and then B. I'm going to tell you this in a little bit again, but it doesn't matter if you use square brackets or round parentheses when we're grouping things together. Either one is a grouping symbol, a set of grouping symbols, and it doesn't matter which one we use. And you can switch back and forth. Yeah, so here we are grouping that, but now this is simpler, so I'm just choosing parentheses instead. I don't mean to confuse you with that. And then we have to reassociate again, B, B, and then have A squared, and finally B squared. So later on, when we go over this property of exponents in a different video, I'm just going to say, well, this is what's going on. But behind the scenes, there's a lot of stuff that is going on. Uh, this is the definition of the exponent that is going on. We have to reassociate. So we're using an extended rule of the associative property um, of multiplication. Then what did we do here? We use the multiplicative property, rather the commutative property of multiplication to switch those two around. Then we reassociate again. So we are using the associative property of multiplication. We are using definition of exponents. We are using the associative property of multiplication. And then we're using exponents, the definition of exponents again. So just to go from here to here, there is a lot of stuff that is going on. I don't think this is trivial. I don't think this is super simple. We make it simple, but it is not really that simple. That brings me to the order of operations. Okay, so order of operations, also known as PEMDAS. Some people have used this, and that's okay. So the first thing that we have to do, or we have to give priority to, is parentheses. Now, by parentheses, we mean any order, rather any grouping symbol. So give priority to grouping symbols. And the grouping symbols that we have are usually parentheses, but we can have brackets, and there's other grouping symbols we may use. By the way, so this is the first thing we do. Whenever you see an expression and you scan it, look for those. If there is nested parentheses, one inside of the other, then we start with the most nested one, the most inner parentheses, or the most inner grouping symbol. There is something important. Every time you have a horizontal line, there are grouping symbols going on. So for instance, when you have a fraction, everything in the numerator is grouped together, even though it is not written as such, and everything in the denominator is grouped together. Yeah. So whenever we have a horizontal line, that is going on. So those are perhaps hidden. Those two could be hidden, perhaps hidden, but they are always there. Sometimes they're explicitly there, and sometimes they're not, in which case we have to assume they are there. That's why back here in this example, example 6, we did 3 plus 5 first. Why didn't we cancel that out? Because there is a parenthesis that is hidden here. It's understood that operation has to be performed first. And by the way, going back to this example, if you have 3 plus 5 over 5, that is absolutely not the same thing as that. Those are completely different things. Because I'm going to come back to this example in a moment. I have to explain why as we go through this list of things. So the first thing that takes priority is grouping. Otherwise, if we don't have a list of priorities, then things are going to be ambiguous. Then we got exponents. And those of you who have seen this PEMDAS, you know that we have parentheses, which we really mean by that is grouping symbols, and there are some hidden grouping symbols. Exponents has to be performed also immediately after. Okay, now I want to talk about multiplication and division. Multiplication and division have the same priority. Multiplication and division. But I have to elaborate on this. Let me give you another example. Example 8. Okay, say you have a, 100 divided by 5 times 2. Okay, or same thing as 100 divided by 5 times 2. Now, if we simply say that multiplication and division have the same priority, then somebody could say, well, let's multiply 5 times 2, which is going to give us 10. 100 divided by 10 is 10. So somebody could say, well, the answer is 10. But somebody else could say, wait a minute, 100 divided by 5 is 20. Then multiply that 20 by 2, and that gives us 40. So simply saying that they have the same priority is not totally correct, because there are cases where that could cause an ambiguity. Which one is the correct answer? We cannot have an ambiguous situation in mathematics. So in this case, we say that they have the same priority, except that if there's no extra parenthesis, we're always going to go from left to right. Yeah, so from left to right wins over multiplying first. So left to right is what we have to do, and consequently 40 is the correct thing to say here, not 10. Yeah. And that's why in this example 6, when I was comparing to this, the answer here would be 4, because we go, well, no, I haven't got to this because I have to compare plus or minus compared to the division. We haven't done that yet here in the list of things we have to do. So multiplication and division have same priority from left to right, though. Whenever there is a competition between the two, comma, we have to go from left to right. All right, so that is the M and D of PEMDAS. And then the A and S, addition and subtraction. Addition and subtraction, okay, have same priority, comma, from left to right. But the way we write these bullets is such that the grouping symbols, if there's a competition between those two, the grouping symbols wins. This has to be done first. If there's a competition between those two, that wins. If there's a competition between those two, that wins. And if there's a competition of any one above and with one below, the one above wins. So multiplication and division compared to addition and subtraction, that wins. That has to be done first. So where's my example 6? So in this example here, there's a competition between addition and division. That wins because division is above addition and subtraction. So we have to perform this operation first. 5 divided by 5 is 1. So this is 3 plus 1. So the answer is 4. So we gotta be very careful especially when you draw a diagonal. I really dislike personally diagonal for fractions because it opens the door to misreading what we are writing down. Are we going to multiply here or not? That's why I prefer not to use diagonal fractions. If you do use diagonal fractions correctly, then you're okay. So for instance, if you really mean to divide 100 by 10, so let's do it, well, versus 100, and you want to multiply first, then as long as you put parentheses, then you're okay. You're golden, you're good. Okay, but if you don't put the parentheses, then you're going to get the wrong answer. And some of you may say, wait a minute, I just missed by a parenthesis. But that's exactly what we are testing, whether you know when to use or the proper use of parentheses or not, or the proper notation. Yeah. Yeah. The next thing I want to talk about is absolute value. The absolute value of a number is simply the positives of the number. And everybody knows, example 9, if you put the absolute value of negative 17, of course, is positive 17. That is not the problem. But when we have, example 10, things like 3 minus 8 and the absolute value, that gets a little more complicated. Are we doing the absolute value of 3, the absolute value of 8, or how are we doing this? Well, this is a trick. Whenever you have an absolute value, pretend there is a parenthesis included in the absolute value set of bars. So really, this means 3 minus 8, do that first, whatever it is, then, which is negative 5, and then obtain the absolute value of that, which is 5. Okay, so pretend there is a parenthesis, or pretend that the absolute value bar also works as a parenthesis of the expression inside of it. Yep. If you have a negative in front of the absolute value bar, well, the absolute value of 5 is 5 itself. So we simplify this by 5, but then we gotta keep the negative, because this, even though the absolute value is always positive, anything that happens after the absolute value will affect the absolute value itself. So this negative says we're going to do the opposite of whatever this is. Yeah, so the absolute value only affects what is inside of the absolute value bars. Whatever is outside of the absolute value has no control over that. So things can get complicated very quickly because we are starting adding or composing absolute values with negatives inside, with negatives outside, and so forth. I have always thought that math is simple if you only look at the simple ideas. Each one of the ideas in math is simple. What makes math quite complicated is that there are many of them, and then you can combine them in many different ways, many different ways. So I think that is part of the reason why math gets to be complicated. Example 12. If you have x minus 4 as is, just standing like that, can we simplify it? And the answer is no. This cannot be simplified because we do not know. Boy, I should have written this in a different, at the beginning of a page. We do not know whether x minus 4 is positive or negative. Sorry to write all of this explanation in a small space. Okay, so can we simplify the absolute value of negative 17? Absolutely yes, because we know the value of negative 17. Or 3 minus 8, we can easily compute that. Or 5, the absolute value of 5 is 5. But if we have a variable and we don't have additional information about the variable, then no. Now, having said that, can we simplify this? Okay, absolute value of x minus 4, whoops, I didn't mean to put a parenthesis. Let's close the absolute value symbol. There we go. Simplify this. Okay, so simplify, comma, assuming x is greater than 10. This is part of the problem I'm providing. Oh, X is greater than 10. So if we know that as part of the problem, if somehow we got that information from somewhere, then sure, we can simplify that. The absolute value of X minus 4 will be X minus 4, but only under this condition. Well, there's many other conditions. If we knew that X was bigger than 11, same thing, or bigger than many numbers, bigger than 5, even bigger than 4, we would be okay. On the other hand, let me write it differently, because the way I wrote this problem is kind of backward. This should have been on top. Simplify this, assuming that. Let's write it correctly. Simplify absolute value X minus 4, comma, assuming that X is less than 20. Okay, now let's think about this for a moment. How much is X? We don't know. However, we do have partial information about X. We know that X is less than 20. So if X was a person and 20 was the age, we know this person cannot have alcohol because it's less than 20. So who's this person? We don't know. But we know that this person is underage for alcohol purposes. That's just a silly example I came up with. All right. So we know this is less than 20. Who is it? How much is it? We don't know, but we do have some partial information. So whatever this number is, take away 4. Well, that number is for sure going to be less than 24. There is a property. So yeah, -4 is equal to -4. And if we add those two together, X plus -4, which we write as X minus 4, the inequality is going to be preserved. 20. Oh, I'm sorry. I meant to put a -20 here. So that under H was not. No, let's keep it like that. Sorry to flip flop on you. So we know that X minus 4 will be less than 16. Can we simplify this? No, because I don't have enough information about the quantity X minus 4. So we cannot simplify, and by simplify, we mean getting rid of the absolute value of X minus 4, because X minus 4 could be positive or negative. The only time we can simplify absolute values is if we are certain of the input in the absolute value. If the input is positive, leave it alone. If the input is negative, do the opposite. Example 15. Okay. Simplify absolute value of X minus 4, comma, assuming X is less than -20. Now, this is the one I intended. The other one was not a big deal to have that example. Okay, so just as before, add -4 to both sides of the inequality. So we have X plus -4, also known as X minus 4. And -20 plus -4, we're going to add -20 plus -4, that is -24. So we are aware, we're conscious that this quantity is less than -4, for sure less than 0, and consequently the absolute value of that is not going to be itself, it is going to be the opposite. So in this case, we do simplify. Absolute value of X minus 4 is equal to the opposite of the quantity X minus 4. Yeah. So do we know the value of X? No, I only know that it is less than -20. So it could be -30 or -21 or -20.1. If we take away 4, that's going to be even more negative. Let's say this is negative 30 as an example. Negative 30. So if this is negative 30 minus 4, we're going to end up with negative 34. What is the absolute value of negative 34? Well, if this is negative 34, if we put another negative in front of it, that's going to make it positive. I know this is a little confusing, but if we know that the quantity is negative to start with, the opposite of that quantity will be positive. Oftentimes, I use this symbol in two ways. So there's two ways to think of this symbol. If we put it in front of a number, a solid number like 5, then we think of it as negative 5. But if we put it in front of a number for which we do not necessarily know whether that number is positive or negative, sometimes we use negative x, but technically speaking, it should be the opposite of x, because we don't know whether x will be positive or negative. If it is negative, its opposite is going to be positive. If x is negative, its opposite is going to be positive. But if x is positive, its opposite is going to be negative. So whatever x is, we're doing the opposite. In this case, we already know 5 is positive, so the opposite is going to be negative. I know it is a little confusing. I don't mean to confuse you with that, but I just want to elaborate on that symbol. Yeah. And that explains why. And the reason for doing that is because here we're using that symbol to denote the opposite of this number, which we know will be negative because that number is less than negative 24, which is already negative to start with. All right, with this, we close this video.